This video is a recap of the conversations we've had about Algebra Review 2. We spent time discussing the idea of a polynomial. Polynomials are an algebraic expression that we find in many places in actual phenomena, and we can use the mathematical version of the events to understand the causes and how we might affect the outcomes. But in mathematical terms, a polynomial is an algebraic expression. It contains terms, and each term is separated by a plus or a minus sign from the other terms. Each term has a coefficient and an exponent value. The coefficients are limited to real numbers, and the exponent values are limited to non-negative integers. Now, we do have algebraic expressions where those constraints are relaxed, that we allow ourselves to have negative exponents, fractional exponents, and we also might have coefficients that are not real number coefficients. But for purposes of definitional clarity, we define a polynomial in the way that I've just mentioned. Now, we do use the idea of factoring a polynomial, which is to take and express the polynomial not just as the sum and difference of the individual terms, but to rewrite it in factored form, meaning terms that are multiplied together that result in the same polynomial when you recombine them in multiplication. We do that in several methods. There's what we refer to as a trial and error method. We use formulas. We use complete the square and greatest common factor. Complete the square is primarily for second degree polynomials. And we also use the idea that if we take and set the polynomial equal to 0 and then factor it, and then we have the individual factors that are equal to 0, we can usually more easily determine the values that make the factors equal to 0, which in turn would make the original polynomial equal to 0. Then this gives us an idea of the behavior of the polynomial, axis intercepts in the graphing scheme. We also can use that solution as a way to find the value for polynomials when we're seeking a value that's not equal to 0. So we can use it for both activities. Division algorithm, this is really nothing new. We're simply saying if I can take a value and divide it and get a result. So we'll do the same thing. We'll take a function, and if I can find something that will divide into that function, meaning a factor, times we call this a quotient, times an additional factor plus a remainder, we can rewrite our polynomial in that form. Now, if the remainder is equal to 0, as this example with numbers is, I know that I've found factors. So we're going to use the idea of having remainders equal to 0 when we do polynomial division to identify whether or not the terms that we're using are in fact factors of the original polynomial. The remainder theorem says that if you do this division and you divide a polynomial by a term that contains this linear expression, x minus c, then what you're going to discover is that you get a remainder, then the value of the remainder is the same result you would get as if you replaced c in the original polynomial and evaluated it for c. We'll see some examples of that as we go along in here. This is sort of a restatement of the fact that if you can find a value c that makes the polynomial equal to 0, then x minus c is a factor of the polynomial. And so what we realize we're doing here with this x minus c is we are saying we're going to set that equal to 0, and we get x equal to c. And so we would be looking for these linear factors to express our polynomial. Now, this is an important idea, and we'll see this on a couple of slides, but if a polynomial has a certain degree, n, then we're going to find that the number of factors, and you'll see those described as roots, zeros, they may sometimes be referred to as x-axis intercept, if it intercepts if we have access in the real number system. But for example, a third degree polynomial, meaning the largest exponent value, if it's a 3, then that polynomial will have 3. So remember, we said that the leading term here is where we find the largest exponent. These exponents are in declining order. So this exponent, if this is a 3, then we know that when we look for the factors to express the polynomial in factored form, we should be able to find 3 factors. Now, occasionally we find factors or values that contain a complex number that includes a value for b as a real number. So we do have a case where we'll have some roots that are considered to be imaginary roots. That is, we can't see them in the real number graphing plane. If you have 1, you're going to have its conjugate. And the reason for that is, if you recall, that if we multiply a plus bi times a minus bi, then what happens in that multiplication process is the I values cancel out, and we wind up having just real numbers. And so that's important because we want to make sure that the polynomial that results in the multiplication has only real number coefficients. Now, this phraseology here, so where it says it has at least one complex root. Now, they don't mean that every polynomial will contain a root that has a real number value for b. In other words, we don't always have roots or factors that include an imaginary value, because you can make the case that since a and b are real numbers, that if b is 0, then what do I have? I just have a. So I could say a plus 0 times I is in fact a complex number. Also, if you recall that the overall definition of complex numbers, we have real numbers, and we then have what are referred to as imaginary numbers. That's the name that's given to values that contain I. So a number, like a real number, is included in a complex number family, and so therefore that's what they mean here. Now, this linear factorization theorem is saying you should be able to take every polynomial and separate it out into a series of linear factors with a value, constant value at the front that multiplies through the terms. And so you'll notice that each of these is a coefficient of 1, and each of these are linear factors, meaning an exponent of 1. So if you have a 3rd degree polynomial, you would have 3 of these. If you had a 4th degree polynomial, you'd have 4 of these, etc. And it says here, an nth degree polynomial can be expressed as a product of a non-zero constant, that's a sub n, and n linear factors, where each linear factor has a leading coefficient of 1. Linear factors means that these exponents on x are 1s. Now, here is one example problem that we discussed, and I think what I'm going to do is I'm going to pause the video and I'm going to work through the solution for this problem. Now, the solution set is in the media that's in the course material. You can look at the PowerPoint slides that are in there and you'll find the solution. But I'm going to pause the video, do some work, and come back and we'll discuss this as I worked it out. All right, so did the work, and what did I do? Well, I said, let me use synthetic division, and in the slides, we saw that one of the candidates for the values was 1, minus 1, 13, and minus 13. So I picked 1, and I used synthetic division, and when I use synthetic division, yes, I get a remainder of 0. So what does that tell me? It now tells me a couple of things. It tells me that 1 is a value that makes this function equal to 0. And you could try that on if you want to. 1 cubed is 1. Minus 5 times 1 squared is minus 5. So what have we got here? 1 minus 5 is minus 4. Minus 13 is minus 17, plus 17 times 1 is 17. So, yep, this value does, in fact, make the polynomial equal to 0, and it corresponds to the value of the remainder being 0. Now, the resulting quadratic that we get after we do this means that this polynomial here can now be factored into x minus 1 times this quadratic. And you say, well, what about the quadratic? Can we factor it? And you'll notice that trial and error factoring will probably not get us anywhere, but mainly because we'd be looking for something that multiplies together that gives us 13 and combined gives us minus 4. So you could use either the quadratic formula, which is one side of the notes, and just plugged in, and I get that the value that we would use is 2 plus or minus 3i. The other approach was to use completing the square. If you recall how to do that method, and we get the same result. That's 2 plus minus 3i. Now, what does that mean? It means now that I need to take and create factors from these values. So I've already done it here. X minus 1 is the factor that is associated with positive 1. So what do? We say x minus 2 plus 3i, x minus 2 minus 3i, distribute the minus sign through here, and you get that the factor that I'm looking for here is x minus 2 minus 3i times x minus 2 plus 3i. Now, let's pause the video again, and what I want to do now is I just want to do some checking and see if these results check out. All right, so the check step was to replace the values that we had for the factors here. So we had a factor of x minus 1, a factor of x minus 2 minus 3i, and a factor of x minus 2 plus 3i. And so when we multiply all this together, we should come back to the original polynomial, which it does. So you can kind of follow through the little tedious computations here. Some of them just you take and I squared this, and so I got x times x is x squared, minus 2x plus 3ix minus 2x plus 4 minus 6ix, and so forth, minus 3ix plus 6ix, minus times a plus is a minus, so that would be minus 9i squared. I squared is minus 1, so it becomes plus 9. So then you collapse this down, and then you multiply through by this, which is, this is the factor that doesn't have any imaginary content, and lo and behold, you wind up getting the original polynomial back. So what that tells me is, it tells me that yes, when I substitute the factored form, these three factors, as I was third degree polynomial, I was going to find three factors. When I substitute those three factors, multiply them together, I come back to the original polynomial. I'm going to pause the video just for a second again. All right, and so the last check step, and it wound up being fairly tedious. So what I did is I said, well, I should be able to take I just did one of the factors that had the imaginary values in it. And so one of that factor was x minus 2 minus 3i. Set it equal to 0 and solve it. Set it equal to 0 and solve it. And so then I'm going to replace x in the polynomial with this value. So it's 2 plus 3i to the third minus 5 times 2 plus 3i squared plus 17 times 2 plus 3i minus 13, etc. So when you go through and you do the expansion and you find that 2 plus 3i cubed is 9i minus 46, and then multiply the result from the 2 plus 3i squared, which was what, minus 5, let's see, minus 5 plus 12i, I think is what that was. Yeah, minus times minus, this one was squared, was what, minus 5 plus 12i. So the multiplication gives me 25 minus 60i, 17 through here, minus just combine your like terms, yay, and you finally, all the i's cancel out, and 59 minus 59 is 0, so 0 equals 0. So both ways that we could check, we checked and got the same polynomial here, And we just took one of those and plugged it in. Had we done the other one, we should have gotten the same zero. Just didn't see any need to do it at this point. So this is an illustration, though, on how you would check a problem if you have these imaginary roots here. You need to treat them as you would any other value that you are evaluating a variable for. So let me pause this one more time. All right, and so the final thing that we did with this polynomial, the x to the third minus 5x squared plus 17x, is we actually used Desmos, since I hard copy printed the Desmos graph out. Yes, you could do this in your graphing calculator. I like Desmos because it's easier to manipulate and to add values and change your window settings. And so this is the Desmos graph, and you'll notice that here is the value of x that made the polynomial equal to 0 in the real world, in the real number system. Now, we know we did have these other two values that we talked about of the 2 plus 3i and 2 minus 3i. We have those other two values which don't show up on this graph because this is a graph of the real number system. Just one other little point, you'll notice that the y-intercept is down here at y equals minus 13. And also, Desmos does give you a table. I didn't try to do anything with it much, other than it did show that when x was 1, y is 0. So again, we had to do some calculations to find the other two roots. We had one pretty clearly here, but we did have two imaginary roots, and we were looking for 3. All right, the last conversation that we had was we talked a little bit about the kind of problem where you're given information about a polynomial and you're asked to determine what is the equation of the polynomial. And so the example was polynomial has, it's a third degree, so we know we're looking for 3 of them, three factors, 3 roots. One of them is minus 3, and we have I as a 0. So you'll have conjugate pairs, so if I is a 0, minus I is going to be a 0. So what we wound up doing with this is simply saying, and they told me that when I evaluate the function for 1, the answer is 8. And so the steps are pretty simple. You just say, well, here's the factored. If this is the 0 minus 3, factored form, it's x plus 3, x minus I, x plus I. When you multiply this out, you can see what happens. You get the i's cancel as we'd like. Finally, you get to this result here. Now, the finishing step on this is they told me that when the function evaluated at 1, it's 8. So you just come back and say, well, I know that the function evaluated at 1 is equal to 8, which is equal to, and I'm trying to find this thing, a sub n times, and then you replace 1 here, right? So 1/3 plus 3 times 1 squared plus 1 plus 3. And so what is that? That's 1, 4, 5, 8. So 8 is equal to a sub n times 8. So you divide 8 by 8, and you get that a sub n is equal to 1. Right? So that's pretty straightforward. It looks more complicated than it is. All right, so we wrapped up Algebra Review 2. I hope this video has helped you. And that's it.